Hello, everybody. Let's fight the flu with Oseltamivir. Oseltamivir. That's how you pronounce it. Which is number 5 on Khan Academy's Biological and Biochemical Foundations of Living Systems passages. So, once I figured out kind of how to pronounce this, I clicked on it, went to the first question: which reactant, aside from sialic acid, would be necessary for neuraminidase to catalyze its reaction? It was a pretty short passage, and it had a chemical structure which made me think, okay, they're going to ask me some OChem, and sure enough, they kind of did. Mainly like enzyme kinetics, though. So I went to find the very first time that they talked about neuraminidase, and it's in the second paragraph. They say neuraminidase is normally found on the influenza virus protein coat and hydrolyzes sialic acid molecules found on the exterior of the host cell membranes to allow newly made viral particles to exit the original host cell and begin infecting other host cells. So, what reactant, aside from sialic acid, will be necessary for neuraminidase to catalyze its reaction? So I felt pretty good about this one because I caught the big hint that they were giving me. They said neuraminidase hydrolyzes sialic acid molecules. So you got this sialic acid there. Only other thing you need, water. Boom. Hydrolysis reactions. Let's do it, people. Okay, number 2. The rate of uncatalyzed hydrolysis of sialic acid is 107 times lower than the rate of the same reaction with the neuraminidase catalyst. What accounts for this difference? Well, for this one, I went up and read real quick in the first paragraph. Transition state analogs are molecules that closely resemble blah, blah, blah. So, Oseltamivir, gosh, I can never remember how to pronounce this thing. Oseltamivir, that's it. Oseltamivir is a competitive inhibitor for the enzyme neuraminidase and prevents neuraminidase from acting on its intended substrate. All right, so they want to know the rate of uncatalyzed hydrolysis is 107 times slower than the reaction with the neuraminidase catalyst. Oh, I totally got that wrong. This one you could 100% answer without even reading the passage. So you choose one answer. You're just looking at what's the definition of a catalyst, basically. And you know immediately you can rule out 2 of these answers because a catalyst, take out neuraminidase and just put in catalyst, does not increase activation energy. Definition of a catalyst is to decrease activation energy. So we know now neuraminidase decreases the activation energy of the reaction, thereby making the reaction more kinetically or thermodynamically. So I kind of took an educated guess on this. I remembered something about kinetically favorable. So that's the one I picked, and it was right. But let's look at the hints that Khan gave us, see if they explain it a little better. So enzymes do not change any thermodynamic properties of a reaction. Well, there you go. I guess I wasn't thinking about it that way. Kinetics versus thermodynamics. It's been a while. Their second hint, reactions with lower activation energies have faster rates. That made sense. So by decreasing activation energy of the reaction, okay. So important thing to remember there, enzymes do not change any thermodynamic properties of a reaction. I can live with that. Okie dokie. At what point does, sorry, this is question 3. At what point does the course of neuraminidase catalyzed reaction with sialic acid? What? Oh, at what point during the course of neuraminidase catalyzed reaction with sialic acid does the substrate most closely resemble the oseltamivir analog? All right, so this one, once again, was a bit of an educated guess, but that's what a lot of the MCAT's going to be, people. You just got to have a sweet background knowledge, be a jack of all trades, and be able to approach questions like this with critical thinking. So, at what point does a substrate most closely resemble the oseltamivir analog? First answer from me is when the energy of the enzyme substrate complex is at its highest point. That one kind of made sense because if you think about the way that an enzyme kinetic works, I don't even remember what that plot is. It's not Michaelis-Menten or Lineweaver-Burke, but it's where you can show the delta G. If anyone remembers what that's called, please tweet at me at the Twitter I don't have. And they always show like you're going up to activation energy and they show that it decreases. However, there's the thermodynamics for you, that the thermodynamics, the start and stop energy do not change. However, the activation energy at that top point, that's the point when you're at your transition state. So when the complex is at its highest point, immediately that sounds right to me. And in fact, it is right. That's the one I picked. Okay, but then the other one. So the enzyme substrate complex is at its lowest point. I guess that could be enticing because you think that, yeah, it wants to choose the lower energy situation or, less complex or something like that. But it's not the right way of thinking about it. And then they say when the complex resembles the energy of the products or the reactants, and neither of those made much sense to me. So real quick, let's look through these hints. Okay, first one, Oseltamivir is an analog of sialic acid's transition state structure. We learned that from the first paragraph. 2, transition states are the most energetically favorable state during a reaction. So transition states are the most energetically favorable state during a reaction. That makes sense, but wouldn't that mean that when you're at your transition state, you would think, like I was kind of mentioning earlier, you'd think that that would mean then like energetically favorable. So like, energetically unfavorable. Yo, people, don't record a whole bunch of podcast episodes in a row when you got a cold because you're going to miss things like that. But you never stop studying for the MCAT. Let's do it, people. Hit it. Let's be doctors. Okay, so transition states are the most energetically unfavorable state during reaction. That makes sense with the with the answer that I had. Please forgive me. The rest of this channel will be so much better. Please subscribe. And then the third one, sialic acid, will most closely resemble oseltamivir when the energy of the enzyme substrate complex is at its highest point, which is the time of the reaction's transition state, which is the most energetically unfavorable state, which is why, like, whenever you see that thing, or your OChem professor, your biochem professor, whoever it was, probably biochem, like biochem 1, they would say, it's like you could go up that slope to reach the transition state, but it might come back down, it might go up, might come back down, and then it might finally just go over. And then that's why if you lower the transition state energy with a catalyst, it's a lot easier to just go over and reach that lower thermodynamic, the lower energy in your products. So that was quite a little journey through that question. All right, question number 4. So if a 5 milliliter sample of 0.1 millimolar neuraminidase is added to a flask containing equal parts oseltamivir and sialic acid, which of the two substrates is more likely to be bound to neuraminidase? Well, we know that if it's a competitive inhibitor and it more closely resembles the transition state, it's an analog of the transition state, then I would say that we are going to see oseltamivir, so that rules out sialic acids. Now we have a 50-50 shot at this. So let's read the first one. So oseltamivir, as it has a greater affinity for neuraminidase, as it can... That's poor wording, Con. Come on, Sal. So oseltamivir, as it has a greater affinity for neuraminidase, as it can more readily bind the enzyme's resting structure, or the same thing, but readily bind the enzyme's transition state structure. Oh, we've been talking about transition state this whole time, people. Just click on that bad boy and hit check. Boom, we got it right. And Sal gave us a nice little validation ring because we called him out on weird wording. Sorry, I'm going a little loopy, people. All right, question number 5. Which fundamental principle surrounding enzymes explains why transition state analogs are able to act as potent inhibitors of naturally occurring enzymes? Well, without even reading this, I would think to myself, without even reading the answers, rather, I would think to myself that if you have a transition state analog that's like a competitive inhibitor with some other substrate and it binds the enzyme, it would bind the enzyme with higher affinity because when the enzyme has to I'm looking at it right now, induced fit theory. Yeah, I kind of cheated a little bit, people. I do all these questions before I record this and I go back through it a second time. But yeah, so the induced fit theory, if you have a transition state analog like oseltamivir that's already there, then it means that the enzyme and the substrate don't have to do the work. It's just the enzyme that has to do the work. Therefore, it's more energetically favorable to bind to oseltamivir. And let's just say that oseltamivir went in there and then didn't let go. It just stayed there and acted as a competitive inhibitor. It's kind of the definition of it. So between all these, enzyme specificity, yeah, kinda, because how else would oseltamivir be binding to the active site of neuraminidase? Allosteric inhibition, no, it's talking about competitive inhibition, which means it's binding to the active site, not an allosteric site. Induced fit theory, that one makes a lot of sense, especially because we keep talking about transition state. The whole idea of transition state came out of the induced fit theory, not necessarily enzyme specificity, but rather the idea that the enzyme and the substrate are going to have to change conformation to fit into each other a little bit. And then the last answer choice, proximity and orientation effects. I didn't even know what that meant, so I didn't look at it. And I clicked induced fit theory, and boom, we got it, people. Let's be doctors.